Welcome back to my channel. My name is Chaki and we are going to solve question number 2.6 from here. This chapter is shear force and bending moment. So question number 2.6 came in the year 2002. In the year gate 2002. Okay, 2000. Now the question is given as a frame ABCD is supported by a roller at A and is hinged at C as shown in the figure below. This is the frame ABCD. A is a roller support and C is hinged, and two forces are acting at this point and this point. This is D. Now we need to find the reaction at the roller end A. The reaction at the roller end A is given by which of the following? So this point is A, this is B, this is C, and this point is D. Length is L by 2, L by 2, L by 2, L by 2, and the total length for AB is L. Okay, and we need to find the reaction at A. Therefore, on giving the reaction, so suppose since this is a roller support, our reaction will be acting like this, the vertically upward direction. This is given as RC. This point is C. Okay. At point A, our reaction in the horizontal direction is given as RA. Okay. We need to find RA. Okay. Now, I'd like to mention is that this is one of the method to solve. That is, we are going to discuss method 1 and method 2 both. So let's start with method 1. In method 1, we are going to consider or apply equilibrium equation. So I can write like this, applying equilibrium equation What are the equilibrium equation? Summation of Fx, that is summation of all horizontal forces, is equal to 0. Summation of Fy, which is summation of all vertical forces, is equal to 0. First, summation of Fy is equal to 0. When we write this, we can write that Rc is equal to, the vertical forces are acting are P and P. Say this point is E. So P acting at E and P acting at D. Therefore, we can write P plus P is equal to 2P. Okay. And summation of Fx is equal to 0. That is Ra, that is the horizontal reaction. The horizontal reaction are 0 because only Ra is acting here. There is no other horizontal forces. Therefore, Ra is equal to 0. Okay, this is our required answer. Of method 1. Now for method 2. we are going to apply the equilibrium equation again, but in this case we are going to apply the equilibrium equation of moment. That is, we are going to write like this. Since this point is hinged, already given to us, therefore we know that moment about hinge is 0. Okay, so we are going to write like this: applying equilibrium equation, summation of moment about z-axis is equal to 0 at C. Therefore, we are going to write summation of moment MC is equal to 0 RA into L. Considering this point, it is at a distance L. This reaction force RA is at a distance L from point C and acting in the clockwise direction. Okay, so RA into L plus say this for this point number D, this PA is acting along L by 2 distance from C. Therefore, I can write P into L by 2. It is also acting in the clockwise direction. However, at E, the point load P is acting in the anti-clockwise direction, that is opposite to the direction which we have considered to be positive. So I'm going to write it as minus P into L by 2 is equal to 0. So after solving, we get that this is cancelling out each other. Therefore, we can write that RA is equal to 0. This is our answer. Okay. So our point is D, point number D, 0. Okay. Now for the next question. Our next question came in the year GATE 2001. Therefore, the question is given as the bending moment in kilonewton meter unit at the mid span. This is the mid span XX, location X in the beam with overhang shown in the figure below. Now this is the beam. This is roller support or hinge. There is a spring acting here at this point. A load 10 kilonewton is acting this direction and a 20 kilonewton load is acting at this direction. So we don't know if the beam is going like this or like this. So to know this, that is to know the deflected shape of the beam, we need to consider the free body diagram. So on to with the free body diagram, question number 2.6, 2.7. We are going to draw directly the free body diagram. $20 kilonewton. Here, the reaction force acting RA. Okay. This distance is 1 meter. This distance is also 1 meter. Also, at this point, a 10 kilonewton load is acting. At this point, there is the spring, but the reaction of the spring we are going to write like this. This is RB. Okay, this is 1 meter. This is also 1 meter. This point is C. This point is A. This point is B. And this point is D. This is the free body diagram, FBD. Now, or should I say, to solve this beam and to find the deflection or moment at XX section, we are going to taking summation of Fy is equal to 0. Therefore, we can write that Ra plus Rb, the reaction forces in the beam, Ra plus Rb is equal to 20 plus 10. 20 plus 10 kilonewton is equal to 30 kilonewton. Okay, this is our equation 1. Also, we are going to take summation of moment about A. Summation of moment about A is equal to 0. Here we are going to write Rb into 2. From here, Rb is acting at a distance 2 meter in the counterclockwise direction, anti-clockwise direction. So Rb into 2 minus, this is acting 3 meter from Ra and it is in the clockwise direction. So minus 10 into 3 plus, this is in the anti-clockwise direction, 20 kilonewton load. So 20 into 1 is equal to 0. After solving, we get that Rb is equal to 5 kilonewton. Therefore, Ra is 25 kilonewton acting upward. This is also acting upward. Okay. Up till this point, it was very simple. Now, moment mx is equal to, that is about this section. We are going to consider the right hand portion, that is from here to here. So we can write like this: minus 10 into 2. 10 is the load kilonewton, minus because it is acting in the anti-clockwise clockwise direction. So minus 10 in minus 10 into 2 plus Rb is 5 acting in the anti-clockwise direction at a distance 1 meter away from it. So this. Therefore, solving, we get that it is minus 15 kilonewton meter. Okay, this is our answer. Sign convention, let me write the sign convention. This is note, write it as note. Note sign convention, anti-clockwise, clockwise. Anti-clockwise is always positive and clockwise is negative. This is general. This is important, and this is generally it is anti-clockwise as positive and clockwise as negative. In cases you can also reverse this, but in general we always consider anti-clockwise to be positive and clockwise to be negative. Okay, so our option is option number 15, option number C, minus 15. Okay, for question number 2.8 came in the year 2002. Okay, 2002. A beam is given to us and two statements are given. The member AB carries shear force and bending moment. So first from the question, for the load given in the figure shown below, two statements 1 and 2 are made. Member AB carries shear force and bending moment. This member AB carries shear force and bending moment. Member CB carries axial load and shear force. So which of the statements are true and false? Either both true, both false, one is true, two is false, or one is false, two is true. Okay. So first, to do this kind of equation, we need to draw the free body diagram of a beam. Let us draw the diagram first. Question 2.8. This is the load W. This point is B. This point is C. This is D. And this is A. This is E. This is A. Okay. Reaction are taking place like this. Okay. Now, in this case, we need to draw the free body diagram of part of the beam. So, separately, we are going to draw the free body diagram of AB, BC, and DE. But in this case, we only need AB and BC. So, we can write like this. Free body diagram of member BA the reaction is taking place like this. So the reaction W. So here, when the load W is acting like this point is B, this point is A. The reaction is actually taking place in the moment is actually taking place in the clockwise direction. Okay. So therefore, at the end B, a counterclockwise moment will be acting like this. This is the counterclockwise moment or anti-clockwise moment. This is given as MB, which is equal to W. Say, let this distance be X. Okay. Therefore, it will be W into X. Similarly, at the end B, a load will be acting in the opposite direction of the applied load W. Okay. Now, from load transfer mechanism, we are going to draw the free body diagram of BC. So, in this case, let us draw the free body diagram of BC. This is C. You can write that free body diagram of member BC. So here we can apply the load transfer mechanism, or just we are going to transfer the load mechanically. This is the load W, and the moment here in this case would be in the clockwise direction. This is the moment MB, which is W into X. Okay. Similarly, at the point C, a reaction moment will be acting like this. MC is equal to MB. The magnitude is same, but the direction is reversed. Okay. Now, from both the diagram, we are going to write certain conclusion that the member BA, here this is the member BA, is actually carrying both shear force and bending moment. Since at this point a moment is acting, so we can write like this: BA carries shear force and bending moment. Okay. And from here we can write that the member BA is actually carrying axial load. Now, first of all, the load W is passing through the longitudinal axis of the beam, or longitudinal axis of the column BC, part BC. Therefore, only axial load is acting here. So we can write like this: BC carries axial 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 load and bending moment, but no shear force. Now if we see the statements, AB or BA carries shear force and bending moment, so this is true, and member BC carries axial load and shear force. No, it should have been bending moment, so this is false. So 1 is true, 2 is false. 1 is true but 2 is false. So our option is option number A. Okay. Now for the next question, came in the year GATE 2003. A carved member with a straight vertical leg is carrying a vertical load at Z as shown in the figure. The stress resultant shown in the XY segments are the resultant forces acting in the XY segment: bending moment, shear force, axial, bending moment, axial force only, bending moment, shear force only, and axial force only. Now, this is actually very easy, but let me explain here. Say this is the load W here acting at this point. Okay. Now, this is the line of action. The W load which is acting at point Z passes, its line of action is actually passing through the longitudinal axis of the segment XY, that is eccentricity is 0, such that if we omit this section, this curved section, the load which is acting is like this. This is the load W, this is section X, and this is section Y. The curved portion has no effect in the XY segment. So we can write like this: 2.9. The load W passes through the longitudinal axis of the member XY. Load So we can write, it means that is eccentricity is 0. Okay, therefore, so XY segment axial force. So the XY segment only carries axial force. Okay, since the eccentricity is 0, there is no eccentricity. This is the load W. This is X, this is Y. Okay, there is no eccentricity. If there was eccentricity, it would have been like this. So this is the same segment. This is X, this is Y. Load has to pass through either this direction. Therefore, we can write that eccentricity was E. Okay. Then this might have carried both axial as well as shear force, or bending moment and axial force. But in this case, that this is not taking place. Only this is taking place. That is, the line of action is passing through the XY segment. Here load W passing through the longitudinal axis of the member XY. Here we can write like this: the load W line of action is passing through the longitudinal axis of the member XY. Okay. Question number 2.9. Our option is option number D. Okay. Now for the next question, question number 10. Question number 10 is very, very important. This is a must question. Very important. Question number 10 is probably the last question in this video. From question number 11 we will do in the next video. Now, this question came in the year GATE 2003. Came in the year GATE 2003. It is not that of a tricky question, but still it's an important one. A very important one. The question is given as, the list 1 shows different loading acting on the beam. Okay, this list 1 contains all the different types of loading acting on the same beam. And list 2 shows the bending moment distribution. This is the moment distribution. Match the load with the corresponding bending moment diagram. Okay, this is actually easy, but still it's important. We are going to take option number C or B. which of these first? Option number, let's take option number B. Okay, this is a simply supported beam with a point load acting at its centroid, right? Therefore, this is actually a sagging, it is creating a sagging bending moment. The beam is actually sagging like this, right? So we know that the bending moment in this case is positive. Therefore, the bending moment diagram will be like something like a triangle. That is, so this is point P, this is A, this is B, or whatever. So the bending moment diagram will be like this. Okay, this is the baseline. And anything above the baseline is positive. Okay, therefore option number B is actually corresponding to option number 4. So we are going to write B4, that is either this or this. So we are going to omit option number A and C. Okay, here there is a notable difference, is that if this is the baseline, what is taken is that below the belt it is taken as positive, that is, this is positive. Okay, below the baseline, everything is positive, and above the baseline it is negative. Okay, this is the trick they are using to confuse the student, nothing more. Okay, now for option number C, from this given question we can see that it is either option number B or option number D, right? We can see that C is 1. C is 1. This is a parabolic. P-A-R-A-B-O-L-I-C. Parabolic curve. 2-degree parabolic curve. Okay. Option number C. And it is also positive. So these two have been cancelled out. That is option B, option C, option 1 and option 4. Now we are left with option number D and option number A. Now from this question it is given that option D is either 3 is a 3. Therefore we can write that this is option number 3. This is positive. This is a cubic parabola. Cubic parabola. P-A-R-A-B-O-L-A. That is of 3 degree. Okay. Since the loading here, loading intensity 1 degree. The loading is 1 degree. 1 degree loading. Okay. Now for option number A, it is either 5 or 2. So it is either 5 or 2. Now if we consider this diagram, this is A, this is B. Now the shear force diagram is constant. Okay. This is the shear force diagram. Say this is the moment M, right? Therefore we can write like this, and length is L. This is M by L, the reaction M by L. Okay. The reaction are M by L, and this is it. Now in this case, the loading diagram is given as this. This is the deflected shape of the beam. Therefore, in this diagram, we can see that option or portion AC, this is portion number C, this is portion number C. The entire length is L. So, portion AC is sagging and portion CB is hogging. Okay? Therefore, we can write like this. Since it is sagging moment, anything drawn will be above the baseline. So, first we'll draw a curve above the baseline like this. And since it is hogging, it will be below the baseline like this. This is M by 2. This is M by 2. This is positive. This is negative. Okay. Now this is the bending moment diagram. Bending moment diagram. And this is the shear force diagram. So in this case, it is option number 2. That is A is 2. So our option is option number D. Don't get confused with the sign language. Okay. The sign convention is a bit confusing, but don't get confused. You can simply see that this is a cubical parabola. So this is 3 degree. This is a 2 degree parabola. And this is a straight line. It is of 1 degree. Okay. Just remember this one. Okay, friends, that's it for today. Like my video, do subscribe to my channel. Hope you in the next video. Thank you for watching up till now.